Hello everyone, my name is Dikshita. I'm studying in third year BE, fifth sem at Sri Venkateswara College of Engineering. Today our topic is TOC, Theory of Computation, and my topic is Turning Machines and Automated Stimulators Research. Now let us discuss about the abstract of this topic. Abstraction. This paper introduces a tuning machine and push-down automata stimulators as a virtual environment for learning computational models and automata theory. The twofold contributions of this work is novel use of the modern technology to improve learning and longitudinal experimental evaluation of its use in context. A preliminary evaluation shows the effectiveness of the stimulators in classroom. Now let us discuss the introduction. Computational science is an interdisciplinary field in which mathematical models combined with science computing methods and are used to study the statements systems of real world problems. In practice use, it is typically the application of computer stimulation and other forms of computations to problems in various scientific disciplines. One such of mathematical models is automata theory. The concepts of automata theory, such as tuning machines and push-down automata, have important use in designing and analyzing computational models of several hardware and software applications. These concepts are abstract in nature and hence used to type by a traditional lecture rhyme style, which is suitable for listeners with reflective performances preferences. Since computer engineering learns tend to have a strong active performances, according to Learn the Science research, a lecture-driven technology style is less motivating for them. Our stimulations are designed to tackle this issue and meet their activity learning preferences for computer engineering learners. Our approach can be used as supporting the tools for active learning not only for automata theory but also for several other courses such as theory of computation, discrete mathematics, computational models, programming languages, compiler designers, and other related courses. Such courses cover a variety of topics including the finite state automata, push-down automata, and tuning machines. Literature review of this topic is tuning machines are the most powerful finite state machines. This can stimulate exactly what a digital computers can do. Informally, a TM consists of a finite set of states and a controllers that can read and write the symbols on an infinite length tape. Unlike DFA, NFA, NFA, and PDA, TM controllers can move in both directions on the tape. The machine starts with an initial state of the finite number of inputs symbols written on the tape, and the controllers is a set of first input symbols for the left according to the current state and the current scanned symbols on the input tape. The controllers take the next move. It can overwrite the current scanned symbols or leave it tough would change. The current state then move to either the left or the right and so on. If no more moves are possible, then the machine halts. In some cases, the machine may run forever or and never halt, but more intensively, turning machines can be used to computer functions exactly the same way the modern digital computers can do. In this case, the function arguments are represented as a sequences of ones separated by zeros and are written on the machine state. The finite the function definition is represented as a set of rules suitable for the machine transaction function. Then the machine works on the input if it halts. The input symbol left on the tape represents the value of the function application and on the arguments. Methodology. Turning machines and automated simulations typically employs various methodologies to implement and visualize their conceptual models. Here an overview of and common methodologies tuning machine simulations. Transition function. Implementing the transition function which defines the next state of the tape symbols based on the current state and the read symbol. Tape representation using arrays, linked list, and or and other data structures are represented the finite tape. State management. Managing the states including initial, accepting and rejecting the states. Stimulation loop. Iterating through a computational, updating the tape and state accordingly. Automata stimulators, finite automata, push-down automata, etc. State transition diagrams, visualizing the automata states and transition using the graph algorithms. Transition function, implementing the transition function similar to tuning machines. Input process, feeding input strings to the automation and tracking the acceptance or rejection. Stack management for PDA, stimulating the stack operation, push, pop, etc. for push-down automata. Result, tuning machine stimulators. Tuning machine stimulators are simple online stimulator. Tuning machine visualize tuning machines with these tools. Stimulated tuning machines, JavaScript, an interactive stimulator, automata stimulator, a Java formal language and automated package, a comprehensive tool for stimulating automata. Automata stimulator, stimulate finite automata, push-down automata, and tuning machines. Automata theory toolbox for stimulating and analyzing the automata. Online tools, tuning machines and automata stimulators, an online stimulator for both tuning machines and automata and the formal language stimulators, interactive stimulators and excessive software, tuning world, a graphical tuning machine stimulator, automata stimulator, stimulate finite automata and push-down automata. At last, conclusion. In this work, we introduced the push-down automata and tuning machine stimulators. The purpose was to introduce the active learning stimulators for noise learners of the automata theory and related topics. As an evolution steps, the stimulator were tested by students in the automata classroom. A preliminary student shows the stimulators can improve the learning process of the computer engineering students who study automata theory and related courses. Students express their inter intersect and they judged the stimulators or convenient learning tools for automata theory. Based on the classroom experiences and the students' feedback, we believe that stimulators can be improved in several ways in which we consider in the future work. For example, it will be more convenient for students to run a dialogue during the stimulation process. We also plan to integrate these stimulators into our cooperative automation. Thank you.